Welcome. Today, we're going to peel back the surface of the world around us and look at a technology that is absolutely everywhere, but you'll probably never notice it. It's called embossing. And trust me, it's a surprisingly complex and powerful process that shapes everything from the credit card in your wallet to the very frontiers of optical physics.
All right, so here's our game plan for this explainer. First, we'll cover the basics. What even is embossing? Then, we'll open up the toolkit and see how it actually works. After that, we'll explore the incredible range of materials it can shape, peek into the future at some cutting-edge frontiers, and finally, we'll connect all the dots to really understand why this process matters so much. So let's jump right in with the basics, and you're gonna see this is a concept you're already totally familiar with, even if you don't know the name. I mean, think about it. You interact with embossing pretty much every single day. That really detailed pattern on a nice book cover, or the logo on some fancy packaging. Or, yeah, those crisp raised numbers on your bank card, they don't just magically appear, right? They are meticulously and powerfully pressed into place. And that's really just scratching the surface. The same fundamental idea that gives a cool texture to a piece of cardboard is also being used to create incredibly precise things like microlenses and other advanced optical components. The range of scale here is just staggering. And here we go. This is the fundamental recipe. At its core, embossing is actually beautifully simple. You take a material, you take a patterned stamp or a die, and you apply force. Sometimes you add heat to soften things up, sometimes you don't. But those three key ingredients, material, pattern, and force, that's the heart of the whole thing.
Okay, so let's move on to the essentials and see how this process actually works. Because it's not just about brute force, it's this delicate dance of physics and materials science. And, getting it right requires some incredible control.
So the first big decision an engineer makes is whether or not to turn up the heat. Hot embossing is just perfect for materials like polymers, plastics, or even glass. The heat makes the material soft and flowy, so it can get into every tiny little crevice of a mold. You get this amazing, high-quality replication. Cold embossing, on the other hand, is for the tough stuff, like metal sheets, where you just use pure, immense force to reshape the material at room temperature.
And this isn't just about smashing things together. To get a perfect result without any defects, you have to precisely control a whole symphony of variables. How hot does it need to be? How much pressure do you apply? For how long? Even how fast you press and how carefully you remove the mold. Every single one of these is a lever that can mean the difference between a flawless product and a complete failure.
Okay, now that we kind of know the how, let's dig into the what. The range of materials you can emboss is truly incredible, and each one comes with its own unique set of challenges and amazing applications. All right, so plastics or polymers like PMMA and PLA are the superstars in the embossing world. Think of them like high-tech versions of plexiglass or those new biodegradable plastics. They're used to make things like the tiny channels in a lab on a chip for medical diagnostics or microscopic optical sensors. The big challenge here is getting that melted polymer to perfectly fill every single nanoscale feature of the mold without trapping tiny air bubbles or creating other little defects. Now, let's flip to the other end of the spectrum, metals. When you're embossing a metal sheet, like the aluminum plates inside a hydrogen fuel cell, the challenge isn't about melting. It's all about controlled deformation. Engineers have to design the process so that it shapes the metal just right, without filling it out too much in certain spots, which could cause it to just tear. This table really just pulls it all together perfectly. You can see right here how the material completely dictates both the challenge and the final use. With polymers, it's all about getting that perfect defect-free copy. With metals, it's about managing how it stretches and bends. For super specialized glass, it's about making sure there are no cracks so you can create flawless optics. And then for everyday stuff like paper and leather, it's all about getting that rich detail that's going to last.
Okay, now let's get to the really cool part, the cutting edge. I mean, the basic principles might be old, but the way we're using them now is evolving at an incredible pace, and it's pushing the boundaries of what we thought was even possible. So that classic toolkit of just heat and pressure, it's expanding. Big time. Scientists are now using things like sound, magnetism, and even light to shape materials in ways that are way faster, use less energy, and can create structures smaller than a wavelength of light itself. And this is where embossing really hits the big time, mass production. Instead of just pressing one little piece at a time, roll-to-roll nano imprinting works like a printing press, but for nanoscale patterns. This isn't just a faster way to make things. This is the key that unlocks affordable smart surfaces, letting us turn everyday objects into high-tech devices, like films that create color not from pigment but from their actual physical structure.
And this just gives you a little snapshot of that insane innovation. You've got ultrasonic embossing, which uses super high frequency vibrations to heat and shape a material in milliseconds. Then there's electromagnetic embossing, using powerful magnetic fields to shape metal without even touching it. And athermal embossing, which uses light to draw patterns in special materials, completely getting rid of the need for heat. Just let that sink in for a moment. We are using these advanced embossing techniques to create what are basically smart materials. We're talking about materials that can change their color depending on how you look at them, or even physically change their shape when you shine a light on them. This is where manufacturing meets robotics, but at the nanoscale. It's wild. Okay, we've covered a ton of ground here. So let's zoom back out and connect all these amazing details to the big picture takeaway. Why is this one manufacturing process just so important?
This slide right here really visualizes that incredible range we've been talking about. It's a single technology that works on the macro scale, giving texture to the packaging on a store shelf. It works on the micro scale, creating those tiny channels in a medical diagnostic chip. And it pushes all the way down into the nanoscale, building things like anti-reflective surfaces and those crazy photonic actuators we just talked about. And it does all of this with mind-blowing precision. And some of these advanced hot embossing processes, the replication accuracy can be higher than 95%. I mean, that level of fidelity is exactly why this process is trusted for making things where there is absolutely zero room for error, from life-saving medical devices to high-performance optics. Ultimately, that's the real bottom line here. Embossing is one of the fundamental pillars of modern manufacturing. It's this remarkably versatile and scalable process that quietly adds function, feel, and value to the world all around us, from the most boring, mundane object to the most advanced piece of technology you can imagine. Which, of course, leaves us with a really fascinating question for the future. We've basically developed the tools to impose almost any shape or structure we can dream up onto almost any material. So now that we can make materials look like anything, what new jobs, what new functions are we going to ask them to perform next?